Hello, welcome to the section on non-quadratic losses. So far we've talked mainly about regression. That is the case when the target variable is a real number or a real vector. We've seen several different predictors for such things, including things such as neural networks and simple linear predictors, as well as more complicated things such as trees. And we've seen quadratic losses and a few other example loss functions. And so today I want to go through a few more different non-quadratic loss functions and talk about how the resulting predictors behave when we use those as losses in empirical risk minimization. So when we're solving the empirical risk minimization problem, the empirical risk, the average loss, is simply 1 on n, the sum from I is 1 up to n, of the loss evaluated at y hat I, yi, where y hat I is the predicted value at position xi. So y hat I is g theta of xi. Now, very often the loss function L of y hat y, the intention of it is that it's measuring the discrepancy between y hat and y. How much is the deviation between y hat and y? And so, as a result, it's very common that the loss function looks like a penalty function, p, of y hat minus y. Here, p can take several different forms. We've seen, for example, the square penalty, r squared, where the resulting loss function is therefore the square of y hat minus y. Here, r, y hat minus y, is the prediction error, or the residual. If you've got a scalar y, then r is greater than 0 means that our predictor is overestimating, and r is less than 0 means that our predictor is underestimating. Not all loss functions have this form. We've seen, for example, the percentage error, which had a form which could not be expressed as a penalty function of y hat minus y. So if we have a penalty function, it tells us about how much we object to different values of prediction error. Very often p of 0 is 0, and p of r is greater than or equal to 0 for every other r. Very often p is symmetric. P of minus r is p of r, in which case we really are only determining the penalty based on the magnitude, or that is the absolute value of the prediction error. Sometimes p is asymmetric. P of minus r is not p of r, and in which case we get a different amount of penalty depending on whether we're overestimating or underestimating. Let's look at two common penalty functions. Here is the square penalty function versus the absolute value penalty function. So when we're using the square penalty, that's p of r is r squared, well, when the prediction error is very small, well, then the penalty is really very, very small, small squared. When the prediction error is large, well, then the penalty is extremely large, large squared. If you compare this with the absolute penalty, we'll see that the absolute penalty responds less. For small prediction errors, the penalty is larger than the square penalty. And for large prediction errors, the penalty is smaller than the square penalty. Now here's another one we've seen before when we were looking at quantiles. This is the tilted absolute penalty function, It is parameterized by tau. It's an absolute value, but it's tilted. And so when r is negative, the penalty is minus tau times r. And when r is positive, it's 1 minus tau times r. And tau is somewhere between 0 and 1. When tau is a half, the tilted absolute penalty function isn't tilted. It becomes the same as 1/2 the absolute value of r. So we have the same penalty for underestimating as overestimating. When tau is greater than a half, well then it's worse to underestimate than to overestimate. Remember, the residual is y hat minus y, so the residual is positive, means that y hat is greater than y. And so when tau is greater than a half, well then our penalty is less for positive r than for negative r. And similarly, when tau is less than a half, it's worse to overestimate than to underestimate. Now, the penalty function expresses how you feel about large and small prediction errors, about positive and negative prediction errors. And as a result, they drive the predictor to prefer making certain types of predictions. In other words, the choice of the penalty function is going to change the shape of the histogram of prediction errors. Remember how we construct a histogram? We look at all the residuals and we divide them up into bins, and we display this as a bar graph which shows the distribution of residuals. So here's an example. Here we constructed random data, 300 data records, each one of which has a scalar y and a 30-dimensional u, and then we append a constant 1 so that x starts with 1 and then has 30 random numbers afterwards. And we used a 50-50 test train split here. And here the residual is y hat minus y, so the ith residual is theta transpose xi minus yi. And we plotted here the histogram of the residuals for the predictor that minimizes the empirical risk. And we've done this in two cases. The first case is the top case, where we're using a square penalty. And so this curve here is our penalty function. And we can see we've got some distribution of residuals. And if we look at that in the test data, we get a fairly similar distribution of residuals as we'd expect. Now we also try this with the loss function being the tilted penalty of the residual. So in other words, the loss of y hat comma y is the tilted penalty function of y hat minus y. And what do we see? We see that on the right-hand side of this plot, there's many fewer residuals, many fewer data points for which the residual is positive than there are data points for which the residual is negative, because the penalty is much greater for producing a positive residual, in other words, for overestimating, than for underestimating. And so our predictor, the predictor that is chosen by empirical risk minimization, turns out to be a predictor that prefers to underestimate than to overestimate. And that extends also to the test data, much as we might expect that there's far fewer data points on the right-hand side of the test data plot, test residual histogram, than there are on the left-hand side. Now I want to switch to another type of error that we might want to shape, and that's the case of outliers, and this is called robust fitting. So in some applications you have a few data points that are just wrong, that are just way off. Sometimes this occurs because when the data was entered or transcribed, it was entered incorrectly. There's an error in the decimal point position, or somebody just made a typo. Other times they're caused by sensor failures or various types of anomalies that occurred when the data was collected. And these points are called outliers. And a consequence of having outliers, even if you've got only very few of them, is that the ERM can pick a very poor predictor. Now there are several methods for removing outliers. Here's one. Create a predictor just based on the entire data set, and now look through your data points, and for each data point compute the residual, compute the prediction error. And those data points that have very large prediction errors, mark them as outliers and remove them from the data set, and then refit. If you've still got poor prediction, so a large empirical risk, go through and do it again. This method can work well. It's not easy to implement because one has to decide what it means to have a large prediction error. And it's certainly possible to choose that poorly and not be aware of that. There's another way of removing outliers, or at least handling outliers, and that is to use a penalty function that's less sensitive to outlier data points. And we're going to look at that in this section. These kind of penalty functions are called robust. A robust penalty function is one that has low sensitivity to outliers. And the idea is that the way you make a penalty function robust is you make sure that it grows more slowly for large prediction errors, in particular than the square penalty. And so that means that the predictor will not be predisposed to avoiding those large prediction errors, which presumably occur with the outliers. So they respond a bit more gracefully to the outliers. So instead of the error, in other words, instead of the empirical risk being dominated by the loss at a few very large values of y, because the loss function doesn't grow so rapidly with y hat minus y, those aren't the values that dominate the empirical risk anymore. And we end up with a robust predictor that fits most of the data reasonably well. Now the most famous robust penalty function is called the Huber penalty function. This is named after a Swiss statistician named Peter Huber. And it looks like this. It is a function which is defined in two pieces. First it's defined for small r, and then separately it's defined for large r. And so the transition value will be alpha. And so for r with absolute value less than alpha, it's just the quadratic function. It's just r squared. And for r greater than alpha, it's a linear function. And the slope of that and the intercept of that linear function are chosen so that they meet up very nicely with the quadratic at alpha. And here alpha is 1. And so here we've got a function which behaves exactly like the quadratic. When r is small, when the residual is small, it will penalize the residual exactly the same amount as the quadratic penalty would. But when the residual gets large, it penalizes much less than the quadratic penalty would. And there's an explicit formula here for the Huber penalty. It's r squared when r is small, and some linear function of r when r is large. Let's look at what it does. So here what we have is a simple scalar ERM problem. We have a bunch of data points, and what's plotted here is on this horizontal axis we have u, and on this vertical axis we have v, and we'll have the embedding that x is equal to 1 u and y is equal to v. So we're going to use a linear predictor here. So we're going to use y hat is equal to theta transpose 1u. And we're fitting a straight line to a bunch of data. We have a whole bunch of data points sitting in the middle here. And then we have out here and out here some data points that are outliers. And as a result, if we use the square penalty function, so we solve this problem using least squares, we end up with a predictor which is that straight line there, which as we can see is doing rather poorly at fitting this data set. And we can think about it as these data points are pulling the line down, and these data points are pulling the line up, and we're twisting our predictor. And as a result, even though we've got many more data points that are not outliers than data points that are outliers, what matters is the square of the distance between the predicted value and the actual data point. And so it's the square of the distance between a data point down here and the predicted value up here. That distance squared is how much that data point is going to contribute to the empirical risk. These data points contribute those distance squared. And so even though there are many more data points that are true data points, the distance of the outliers from the predictor is so large that by the time you've squared the magnitude of those corresponding residuals, the resulting terms in the empirical risk end up swamping the true loss terms in the empirical risk. The Huber, if we solve the same problem, but instead of minimizing the empirical risk with a square loss, we minimize the empirical risk with a Huber loss, we end up with a predictor that looks like this. It's still being influenced by the outliers, but as we can see, it's influenced a lot less. And it's doing a reasonable job at the rest of the data as a result. Now you can take this further. You can say, okay, well, I'd like a penalty function which is even less sensitive to outliers than the Huber penalty. Here's a penalty that we might call the log Huber. Again, within a particular region, here alpha is 1, so between -1 and 1, when the residual is between -1 and 1, we've got a quadratic function. And when the residual is larger than that, in absolute value, we've got a logarithmic function. And we can choose the terms in that logarithmic function such that it joins up nicely with the quadratic with the right slope at that point. Notice that even though it says log y squared there, of course the log of y squared is just 2 log y. So we've got something which is quadratic for small y and logarithmic for large y. And that means that when we compare this with the quadratic loss at large R, we're really discounting a lot, very large residuals. We have a diminishing penalty at large residuals, or at large y effectively. And so if we apply the log Huber loss function to our same data problem, to our same data fitting problem, we have here a fit which really passes straight through the middle of the true data points and effectively ignores the outliers. We can see this in terms of the error histograms as well. Here, the top row of these plots show the results from applying the square loss function. Here is our predictor. We can see we've got a residual of training errors. So these are the training residuals, which are spread out between -2 and 2. And we see very similar things in test that we do on train, as we should. In this plot on the left, some of the data points are marked blue and some of them are marked red. The blue ones are the training points and the red ones are the test points. Here's the Huber, the fit that results from using the Huber loss function. We can see that what's happened is that the residuals have split up. Right? There's a whole bunch of residuals that are now very close to 0. Those are the true data points. And we can really clearly see the outliers. And the same thing we see over on test. When we apply the log Huber, we can see that the training residuals near 0 get even smaller and get even closer to 0. We've only got 2 bars rather than 4 bars in the middle. And the same thing in test. So one could, from either the Huber or the log Huber, immediately identify the residuals. And we could simply say, these data points here, we're going to remove from our data set, and then we're going to fit again. And of course, when we fit again, having removed those data points, we could use any one of these loss functions, and it would be fine. It's also important to notice here that when you look at plots like the ones on the left, it's tempting to think, well, why do we need a machine like this in order to be able to identify outliers? And the answer is because here x and y are one-dimensional. If x is in 1,000,000 dimensions and y is in 100 dimensions, well then suddenly we can't make these kind of plots anymore, and we can't see which data points are outliers and which ones are not. Nonetheless, we can still plot the residuals, or at least the norm of the residuals, and the histograms of the norms of the residuals, and be able to identify outliers that way. So the next topic I want to address is quantile regression. The idea here is that we're going to do ERM, or regularized ERM, and we're going to use a loss function which is generated by the tilted penalty function. And that's called quantile regression. And the intuition is that when tau is greater than 1/2, that's going to make it worse to underestimate. And so we're going to end up with predictions that are high. And when tau is less than 1/2, it makes it worse to overestimate. So we're going to end up with predictions that are low. Now, we can be explicit as to exactly how high or low these predictions are. And the way this works is that we're going to assume that the predictor has the form theta 1 plus g theta tilde of x. And that means that, say, theta 1 might correspond to a linear predictor where x1 is 1, and so the resulting prediction has a theta 1 term in it. And we're going to assume that theta 1 is not regularized. The other components of theta might be regularized, and g tilde of theta of x may not be a linear predictor, it's an arbitrary predictor. In other words, that the regularizer r of theta does not depend on theta 1. So we might have bridge regression where we're using the square regularizer, and so r of theta is theta 2 squared plus theta 3 squared all the way up to theta d squared. Now, if you do this, then it turns out that on the training set, when you're using the regularized ERM predictor, the 1 minus tau quantile of residuals is 0. In other words, the fraction of data for which we overestimate is tau. And that's why it's called quantile regression. If the predictor generalizes, and we would expect to see the same thing in the test data that we see in the training data. Notice that in the training data, this is exact, apart from the possibility that there might be data points with repeated residual values. So we can create predictors for many different taus, which give many different quantile estimates for a particular x. So let's look at why we get this phenomena. Remember what we saw in the section on constant predictors. We saw that if we minimize the empirical risk, 1 on n, the sum from I is 1 up to n, of the tilted loss of theta minus yi, that the resulting theta has the property that theta is the tau quantile of the yi's. Now here, we're minimizing something different. We're minimizing 1 on n, the sum over I is 1 up to n, of p tau of g theta of xi minus yi. So that's not quite the same, but let's split it up by using the property of g theta. And that is that g theta is theta 1 plus g tilde theta of xi minus yi. And we're going to minimize this over theta. And that means our problem is minimize over theta, L of theta. Now theta has multiple components, theta 1 through theta d, and we can regard this minimization as equivalent to, minimum over theta 1, minimum over the rest of theta, L of theta. And once we've done this part of the minimization here, what's left is a minimization that looks exactly like the one we had before. It looks like this, where now we have theta 1 plus a term g theta tilde xi minus yi, which doesn't depend on theta 1. As a result, theta 1 is going to turn out to be the tau quantile of yi minus g theta tilde of xi. We can say that another way. The fraction of the data points for which yi minus g theta tilde xi is less than or equal to 0, is less than or equal to theta 1, is around tau. Subtracting theta 1 from both sides gives us the residual. And so the fraction of I for which the residual is greater than or equal to 0 is around tau. The fraction of data points for which we overestimate is around tau. Here's an example. Here we have, again, some random data that we've solved ERM for, where we're using a loss function, which is a tilted loss function. And we can see exactly what we expect to see. When tau is 0.1, 90% of the data has a residual which is less than 0. When tau is 0.9, 10% of the data has a residual which is less than 0. And when tau is a half, about half of the data is one side and half the data is the other side. Let's look at an example of ERM where we're trying to fit data. Here we have a bunch of data points. Again, similar one-dimensional U, one-dimensional V, and we're going to embed by x is equal to 1 U. So we'll have a constant term and a linear term in our predictor. We have got blue points here which are training points and red points here which are test points. And we're going to fit a straight line prediction model using the tilted loss at 3 different values of tau. And these are the resulting predictors. This is tau is 0.1, a predictor for which our prediction at any given value of u, let me pick a value of u, say I pick 0.3, the prediction is somewhere around 1, which is clearly above most of the data. The predictor prefers to overestimate than to underestimate. With tau as a half, we get a predictor that's somewhere in the middle. And when tau is 0.1, we get a predictor that prefers to underestimate than to overestimate. Another way to view this data is to plot the predicted value and the true value for the data points on one plot. So here we have the true value of v or of y, and here we have the predicted value v hat on the vertical axis of each of these three plots. Now in the ideal world, v hat would be equal to v, our predictor would produce perfect predictions, but of course we know that's not very likely, particularly with this data set. And so we see that v hat and v are spread out. So in the ideal world, we'd have v hat and v would be a bunch of data points that would live on the diagonal, and that would be the perfect predictor. If you've got a predictor that tends to overestimate, well then the predictor tends to produce v hats that are greater than v, and that means it tends to produce points that are in this half of the plane. And if you've got a predictor that prefers to underestimate, it tends to produce v hats less than v, and we end up with points in this half of the plane. And we can look at, if this is training data, we can look at our data and count, and we would find that 90% of the points are above the line here, and 90% of the points are below the line over here. And with tau is a half, well then we should see exactly half of the points on one side of the line and half of the points on the other side of the line. So there's another way of plotting this data, and that is to look at the cumulative distribution of the residuals. So for any given Q, we going to plot Q here on the horizontal axis, and then on the vertical axis we will plot the number of data points for which the residual is less than Q. And in particular, I've got three plots here. One shows the residuals when we've computed the predictor using tau as 0.1, another when we've computed the predictor using tau as 0.5, and a third using showing the residuals when tau is 0.9. And if we look at this plot, and we look at Q is equal to 0, the green predictor with tau as a half, shows us that exactly 1/2 of the training data points are less than 0, have residual less than 0. When tau is 0.1, we see exactly fraction 0.9, so exactly 90% of the data points have a residual less than 0. When tau is 0.9, we see exactly 10% of the data points have a residual less than 0. And so here we're seeing that the quantile regression is giving us exactly the quantiles we expected it to on the training data. On the test data, let's have a look how well we did. At Q is 0, we're getting almost exactly 0.1, but tau is 0.9. We're getting 0.45, so we're getting 45% of the data have a residual less than 0, with tau is a half, and we're getting 85% of the data have a residual less than 0, with tau is 0.1. So even on the training data, we're getting quantiles for the residual that match pretty much what we expected to get. Let's summarize. Loss function is often expressed as a penalty function of the residual. The residual is r equals y hat minus y. And the loss function expresses how much we object to different values of the residual. Different choices of loss function give us different ERM predictors. And in particular, there are two types that are very important. One is robust fitting. When you're fitting data with outliers, you use a penalty function which increases more slowly than the square penalty function, and that gives you robustness to the outliers. If you're interested in producing predictors that prefer to overestimate or underestimate the data, then you can do quantile regression. And in quantile regression, you fit data which gives in such a way that you get a specific fraction of overestimates. And you can choose that fraction by choosing tau.